So here's an example of a problem that's both easier, faster, and more precise to solve using triangles than using the FAA's approximation formula. So in this problem, we're given a magnetic, or we're told that we're flying a magnetic heading of 270, and our airspeed's 120 knots. We fly through the 360 radial of a VOR at a certain time, and then we fly through the 350 radial 7 minutes later. We're asked to figure out the time and distance to the station. So this is real easy to set up using triangles. We just draw our plane passing the 360 radial and then passing the 350 radial a little bit later. It takes 7 minutes at 120 knots. So we overlay our triangle on top of all this and label the side that we're searching for. So we're trying to find x. X is the distance from the navaid. Our angle is 10 degrees, and that comes from the fact that we flew from the 360 radial to the 350 radial. And the distance that we flew is 14 nautical miles, which simply comes from the fact that we flew for 7 minutes at 120 knots. So now we've got everything we need. We've got an angle, we've got a side opposite that angle, and we've got a hypotenuse that's unknown. So with those three things, we should be using the sine function. When we plug in our values, the 10 degree angle, the unknown x, or the unknown hypotenuse, and the 14 nautical mile flight path, we solve for x and get 80.6 nautical miles. Easy enough. Then we go back to our question and we look, and we see that 80.6 isn't one of our choices. There's an 84, which is pretty close, but it's not exactly 80.6, and that kind of strikes us as a little odd. Did we make a mistake? Well, it turns out that 84 nautical miles is the correct answer, and we did not make a mistake. Let's see why the answer doesn't match exactly. So the solution that's published relies on an approximation formula, and the derivation of the approximation formula is based on the rule of thumb that 1 nautical mile is 1 degree of bearing off of your navaid at 60 nautical miles out. So if you're 60 miles from the navaid, 1 degree deflection is 1 nautical mile. That's probably a more clear way to restate that. So using that rule of thumb, you can figure out that if you're flying past your navaid and you fly 1 nautical mile past, you should have achieved a bearing change of 1 degree. We can then set up a proportion. So if 1 nautical mile is 1 degree at 60 miles out, then at some arbitrary distance to the station, you can basically assume that it's going to be a linear multiple of whatever the difference in the distance is in order to figure out how quickly you're flying past the station. Okay, so it's just a simple proportion here. If you solve the proportion, you find that the distance to the station equals the distance flown times 60 over the degree bearing change, which is the approximation formula that the FAA uses in solving this problem. So if we plug our numbers in, 14 nautical miles, 10 degree bearing change, we get the answer that shows up in the solution as 84 nautical miles. But it's not exactly correct, because 60 nautical miles is really just a rule of thumb. It's not a precise value. The precise value can be found by drawing a triangle. So if we draw our triangle, we see that 1 degree of needle deflection on the VOR at 1 nautical mile out can basically be set up as, like I was just saying, a triangle. So if we draw an X for our hypotenuse, we have our angle, or our side opposite the angle, and then an unknown for the hypotenuse, which means we're using sine. And when we solve our sine function, we get 57.2. So 57.2 is the exact distance that you have to be out from a navaid in order to achieve a 1 nautical mile, or a 1 degree deflection with 1 nautical mile of cross-track. So now let's plug the 57.2 in where the 60 was in the FAA's formula, and then plug our numbers in and see if we get the correct value. So when we plug in our numbers, which is 14 nautical miles, 10 degree separation, or 10 degree bearing change, we get 80.1. Well, 80.1 is pretty close to 80.6, but it's not exactly 80.6. So there's still some approximation going on here. Why not? Or where is it coming from? So let's dig a little deeper. Well, the approximation formula is based on the idea that at 57.2, and I'm going to add some digits here, at 57.2 nautical miles out from the navaid, 1 nautical mile of cross-track is 1 degree of deflection. It assumes that as you keep flying along that path, if you're 57.2 nautical miles out when you start, it assumes that you're going to keep traveling 1 nautical mile for every 1 degree of deflection you get on the navaid, or every 1 degree of bearing change. But it turns out that's not quite true. As you fly a straight path, your distance from the navaid slowly starts to increase. And as your distance increases, the number of nautical miles that you have to fly to get a 1 degree bearing change also increases. So your second degree of bearing change requires a little bit more than 1 nautical mile of flight in order to achieve it. By the time you get to the 14 point, you're off by over a quarter mile. So you have to fly 14.28 nautical miles to achieve a 14 degree deflection at 57.29 nautical miles out. If you keep going until you get to the 45 degree point, you now have to have flown 57.29 nautical miles to have achieved that deflection. If you wanted to try to achieve, or I should have said bearing change. If you want to try to achieve a 90 degree bearing change, it should be obvious that you're going to have to fly forever. No matter how far you fly along this flight path, you are never going to achieve a 90 degree change in your bearing. You can approach it, but you can never actually get there. So as you get closer and closer to that 90 degree point, the distance between angles is going to increase more and more and more. This is what the FAA is not taking into consideration in their approximation formula. They're just assuming that you're staying close to the abeam point of the navaid. So as you travel a certain number of degrees of bearing change, the distance that you're going to have to fly to achieve that remains constant. That's the assumption that's resulting in the remaining variation between the answer that we got using the trig function, which is the exact answer, and the answer that you get using the approximation formula with 57.29 plugged in. So what does all this mean? Well, for bearing change problems, the easiest way to do it is to just draw the triangle, or use the formula which is shown here, which comes from drawing the triangle. If you just take your distance flown and divide it by the sine of the bearing change, you don't have to worry about any of those limitations of the approximation formulas. You don't have to worry about the 60 nautical mile versus 57.2, and you don't have to worry about the fact that as you get farther from the navaid, the distance between bearings increases. None of that makes a difference because you're just solving the triangle. It's only when you start trying to do approximations that things get tricky. So the easy way to do this problem is really just to visualize the triangle. But if you do that, or if you use the formula that's on the screen now, your answer is going to be about 5% lower than what the FAA, or than what the correct answer in the choices is going to be. And that's because the choices answer was derived using that using that rule of thumb with the value of 60, and that 60 is about 5% higher than the correct value of 57.2. Now here's another type of problem, or here's another problem that tests you on exactly the same concept, except this problem has a significant issue with it. And it can make it very difficult to draw the triangle. Well, not very difficult, but it can make it difficult to draw the triangle if you don't make the assumption that they're assuming that you're going to make. So for this question, you're told that you have a wingtip bearing change of 5 degrees, and you're told that the time to achieve that bearing change was 5 minutes at an airspeed of 115 knots. It then asks you to find what your distance to the station actually is. But there's one glaring piece of information that's missing here. You know that your bearing change was 5 degrees, but you don't know which 5 degrees it was. You don't know where you started with respect to the station. If the station started directly off your wing, then the 5 degree bearing change would have been from, say for example, 090 to 095. You know, if the navaid was directly off your left wing and you were flying due north. But it would be equally accurate, if you're flying due north, to assume that your bearing change was from, say, 015 to 010. That would be correct in accordance with this problem. So anyway, let's look at the solution. So if you assume that the navaid starts directly off of your left wing with respect to your flight path, and you do a 5-degree bearing change, then you can draw a simple triangle and just use the same approach that we used for the previous problem. Plug in your values and you get 109.91 nautical miles as your distance off the navaid. If instead you go the other route and you decide to use the FAA's formula, you use the approximation, you do 9.58 times 60 divided by 5, and you get 114.95 nautical miles, which is about 5% higher than 109.91, so they match up the way we expect them to. You go back to your answer and you circle 115 and you get it correct. But the problem is you made that assumption based on really nothing. There was no reason that the navaid had to have started directly off of your left wing. It would have been equally accurate to assume that you were well past the navaid before you started doing that timing. If that was the case, as I've shown here, and you were actually flying from the 040 to the 035 radial on a heading of 360, then now your problem gets a lot more complicated and your answer is completely different. So in this situation, you don't even have a right triangle to work with. So right off the bat, this starts to look ugly. Since there's no right triangle, you can't start using trig functions until you do a little bit of work in order to figure things out. Now, before I delve into this, I should say that you're not going to need to do this on the exam. I'm only showing this solution to prove a point. So please don't try to follow the math unless it interests you. So to solve this problem, you would extend the course that you're flying, or you're heading, you would extend that down to the abeam point of the navaid. And then now you have two triangles. Notice you have a small triangle inside a big triangle. The smaller triangle has a side opposite of a 50-degree angle with a length that I've labeled as OPP. The bigger triangle has a 55-degree angle, and its opposite side length is OPP plus 9.58. With that, you can set up a system of equations. And the system of equations relates the tangent of the two triangles. When you solve the system, you get a distance of 70.66 nautical miles. That's not even close to 109 or 114. So you had to have assumed that you were starting off the abeam point in order to get this problem correct. If you even went farther north and you said you were flying from the 015 radial to the 010 radial, now your distance is 28.45 nautical miles, which is even farther from the correct answer. So what's the moral of the story? Well, when you're solving these types of problems, if you're going to draw the triangle, you should always assume that you're directly abeam the navaid. If you don't, you're going to get the problem wrong. And you're probably not even going to be able to do it unless you take the time to solve the system. If you're doing this in real life, make sure that it's actually true. So make sure that you really are abeam or close to abeam to the waypoint when you start doing, or when you start your timer. Now what makes this even more frustrating in a way is that in some of these navigational problems, they will explicitly tell you that that assumption isn't true. And then they go right ahead and they make the assumption anyway. So in this problem, we're told that we have an ADF tuned to a non-directional radio beacon and the relative bearing changes from 095 to 100 in 1.5 minutes. So in this problem, you're told that you're not directly abeam the waypoint. You're close, but not quite to being abeam the waypoint. And that you can figure that out because the relative bearing starts at a 095 rather than a 090. So what does that mean? That means if you draw this out using triangles, here's what you got. You've got a plane that's flying from the 095 bearing to the 100 bearing, or relative bearing. And it takes 1.5 minutes. So again, you have no right triangle to work with if you follow the exact, if you interpret the question the way it specifically tells you to interpret it. So to solve this, you're going to have to do the same thing I did for those other problems. You're going to have to extend the triangle down, set up a system of equations, and solve the system. When you're done with all that nightmare, you get 17.145 minutes as your distance. Or I mean, as your distance out from the navaid. When you go back to your question, you see one of your choices is 18, and it also happens to be the correct answer, which is nice. So you move on. But let's see how the FAA did it, because surely they don't want you to go through all that. So the FAA just says to use the same basic formula that you used for all the other problems. So this is the same approximation. It's based on that whole 60 nautical miles out is 1 degree of cross track for every 1 degree of bearing change. The problem is that formula really only holds true, as I showed before, when you're close to the abeam point of the navaid. So why did they go to all the trouble to tell you that you weren't directly abeam the navaid? They could have just as easily had this question be from 090 up to 095, and then it would have been a much more, the assumption would have been more correct. Still not perfectly correct, but not quite as bad as going out of their way to tell you that you're not abeam the navaid. If you'd been farther off, then your answer would have been wildly incorrect. So I've taken this problem and I've crossed out the 095 and the 100 and rewritten it as 170 and 175, just to make the point that as you get farther and farther away from the abeam point of the navaid, the FAA's approximation formula becomes more and more inaccurate. So the correct answer to this question is 2.99 minutes. If it took you 1.5 minutes to achieve a 5-degree deflection from 170 to 175, then that means you're actually really close to the navaid, 3 minutes away. But when you use the FAA's approximation formula and you plug in your values, you find that you're 18 minutes away, which is not even close to correct, because you're too far away from the abeam point to use this approximation. It really starts to break down once you get this far away. So, what's the point? Well, the moral of the story is that for any of these problems, you should assume that you're always abeam the navaid. And the reason you can assume that is because the FAA assumes that as a fundamental pillar of their approximation formula. The entire formula falls apart if you're not abeam the navaid, so you might as well just go ahead and assume that for any one of these questions that you're given on the exam, that your starting point is abeam the navaid. And again, in real life, make sure it's actually true. If you rewrite the question that we started with, assuming that you're abeam the navaid, you'll see that you fly from a 090 relative bearing to the station to a 085 bearing to the station. Now it's simple. Now you have a right triangle, you have an angle, and you have a side adjacent to the angle. All that's left to solve for is the hypotenuse. You can do that using the cosine. Plug in your values and you get an answer of 17.2. 17.2 is still close enough to 18. And it was quick and easy and didn't require you to memorize any formulas.